Okay, so a lab supply company sells pieces of Douglas fir 4 inches long and 1.5 inches square for force experiments in science classes. From experience, the strength of these pieces of wood follows a normal distribution with standard deviation 3,000 pounds. We want to estimate the mean load needed to pull apart these pieces of wood to within 1,000 pounds with 95% confidence. How large a sample is needed? Show your work. Okay, so we're going to use our inequality where we have the margin of error will be greater than or equal to z star times the standard deviation over the square root of n. This is what we use when we're dealing with sample means. So let's go ahead and let's figure out what our z star is. And we already have our standard deviation. And this is pretty much just going to be used in an algebra problem. So we just replace our margin of error with what we're told here, and it says 1,000. So we're going to have 1,000 is greater than or equal to z star, and since we're looking at 95% confidence interval, we're looking for the z star with 2.5% to each side of it. And again, this is a very common one that you probably already have memorized. It'll be about 1.96, but just to re-practice, we're going to look at the inverse norm function with 0.025 area to the left. And there we go. So 1.96. Standard deviation is given to us as 3,000 in the square root of n. Since we're solving for n, we're going to leave it as is. And then now we're going to basically work our algebra. So we're going to divide each side by 1.96. So 1.96, that'll cancel that out. Get that. And then I would divide both sides by 3,000, or you could square. It doesn't actually matter, just whatever you do, make sure you do it correctly. But let me actually rewrite this a little bit neater. So we have 1,000 over 1.96 is greater than or equal to 3,000 over the square root of n. So actually, let's do this. You can multiply both sides by the square root of n. That'll cancel that out. You'll have the square root of n like that. And then on the right, you'll have just the 3,000. And then you're going to divide it by this. So you're going to divide each side by the 1,000 over 1.96. So we have the square root of n. It's greater than or equal to 3,000 over 1,000 over 1.96. Then you square both sides. So you square both sides and you'll get that n is greater than or equal to 3,000 squared over this whole thing squared. And you can do it all at once, or you could do it like broken up. So maybe just do it like squared afterwards. So maybe put the whole thing in parentheses and square that whole thing. So figure out what this value is and square it. So we're gonna have 3,000 divided by, we're gonna open the parentheses, 1,000 divided by 1.96, close parentheses, 5.88. Then we're going to square this, and it'll give us about 34.5744. So n has to be at least 34.5744. And again, since you can't have like this as a number of individuals, you can't have this as a sample size. So we're going to move it up, so round it up. So our sample size has to be at least 35. Okay, problem 9. Explain how each of the following would affect the margin of error of a confidence interval if all other things remain the same. Increasing the confidence level. So let's scratch that. So let's go back to what how a confidence interval works, and let's compare two things. So let's look at like, a normal distribution. Let's say we're looking at, a 90% confidence interval. So that'll be from there to there. Now, understand that a confidence interval, we go from the center, our point estimate, and then the distance from the center, so from here to here, or from here to here, that's our margin of error. So the distance from here to that end and from here to that end is our margin of error. That's just a general concept. So if we want to increase the confidence level, let's say we want to increase it to 95%, our confidence interval gets wider. We're going to say from here to there, that's 95%. And our center's still in the center. Our center's still whatever that value is. But our margin of error gets bigger because the distance from the middle to each end increases. So everything else being equal, assuming that you have the same sample size, the same sample proportion or sample mean, whatever, the margin of error gets bigger as you increase the confidence level. So you can say margin of error increases. Right, now part B, quadrupling the sample size. Okay, so let's actually do some math so I kind of see what's going on. So the margin of error, let's look at this for population proportion. So the margin of error, for the confidence interval, it will be p hat plus or minus z star times the square root of p hat times 1 minus p hat all over n. Remember, this is our margin of error. Margin of error. So that's our margin of error. Now let's think. So let's say this is one of our this is a sample size n. We don't know what n is. We'll just call it n. N could be anything. Now, if we're gonna quadruple the sample size, let's compare this to margin of error where we have 4 times n. So let's see, instead of n, we'll just look at, we only care about this. So let's see what happens when we have z star times p hat times 1 minus p hat over 4n. So how do these two things compare? Like, how does this margin of error compare with this margin of error? The only thing we changed was the sample size. We quadrupled it. And the way this works is using algebra, going back to square root properties, we can break the square root up as the square root of p hat times 1 minus p hat just for the numerator over the square root of 4 times n. You can do that. And furthermore, you can break this as the square root of 4 times the square root of n. Rewriting this. So square root of 4 times the square root of n. And let me actually just so we save some space. So that's like the same as the square root of 4 times the square root of n. But the square root of 4 is just 2. So this is the same as 2 times the square root of n. So this simplifies to that. And if you look at what this is compared to that, what we do to this to get to here is all you do is multiply by 1/2. Multiply by 1/2. Because 1 over 2, that's the same as what we have here. 1 over 2. So when you quadruple the sample size, you cut the margin of error in half, so you can say half the margin of error. Half the margin of error, or you maybe think this is supposed to be halve, H-A-L-V-E. You had the margin of error. If you want to be, grammatically correct. So you cut the margin of error in half. And that makes sense because if you have a bigger sample, you're going to get more precise estimates. So your sample, or your margin of error, or your confidence interval will be smaller. So that means your margin of error will be smaller. So obviously, we always want a bigger sample with better estimates.